Hello and welcome to my presentation. My name is Lukas Lux, and in this presentation I like to talk about the monitoring of gravitational mass movements in alpine regions by markerless 3D motion capture. Gravitational mass movements like rock falls or slope failure represent a significant hazard potential in mountain regions. For better predictability of such hazards, a precise determination of the ongoing mass movements is necessary. A famous example of a current slope failure is the mountain Hochvogel, which you can see on these pictures. The mountain is located in the Alps on the border between Austria and Germany. The summit is characterized by a big crevasse which divides the summit into a stable and an unstable part. The unstable part is in danger of collapse, and there is the risk that it will fall into the valley. To observe the motion of the slope, a large set of sensors was installed at the summit. In this presentation, I want to talk about the photogrammetric observation which we have carried out. The aim of the work is to estimate 3D motion vectors. These vectors should be automatically detectable, have a high spatial resolution compared to manually marked points, and they should be sensitive to detect a motion in the order of several millimeters to a few centimeters. Finally, they should be statistically tested for their significance. On this slide, I would like to show you our workflow. For one epoch, our input data consists of a sequence of overlapping images and some additional ground control points. On the base of this data, we perform a 3D reconstruction. To that aim, we follow the standard workflow of structure for motion approaches. First, we compute some key points and descriptors, then we perform a bundle adjustment, finally we can perform a dense matching. As results, we obtain a dense and a sparse point cloud as well as some feature descriptors. For a second epoch, we use the same workflow, so in the end we get all the results for both epochs. In the next step, we want to perform a change analysis. A common way to do this is to compare the dense point clouds of the two epochs. For example, by calculating the multi-model to model cloud comparisons. The disadvantages of this method is that the obtained distances only can detect changes in the direction of the local surface normal. To solve this problem, we are doing a feature-based co-registration across the epochs. The advantage of this is that we find exactly the same point in both epochs, and so we do not need an approximation of the correspondences. For each key point from epoch I, we obtain a set of image coordinates from the epoch J. From these, we calculate the 3D object coordinates by means of forward section. Finally, we use the 3D coordinates of both epochs to compute some 3D motion vectors. In our experiment, we use a terrestrial platform, simply a camera mounted on a stick, to capture the image sequences. Our image sequences are generated in such a way that they contain areas of the stable as well as the unstable part of the summit. On the stable one, we placed some ground control points, so the image can be registered to a local global coordinate system. We used two datasets, one from 2018 and one from 2021, with 13 images of each year. The used image contained a huge overlap. Approximately, they were taken every half meter. Here, we see an example of all key points from an image from 2021. The potential key points are displayed in yellow. The points that are also found in the past epoch are shown in red. We can see that the key points were found along edges and cracks. In contrast, and as expected, homogeneous surfaces do not show any key points. If we look only at the red points, it is noticeable that they do not occur within debris-covered areas. In these areas, the erosion leads to to two strong changes. In addition, we see that dark shadow-covered areas also make it difficult to find corresponding points. Now we are coming to the estimated motion vectors from 2080 to 2021. On average, the points show a motion of about 73 millimeters in 3 years. When looking at the vectors, we can see that the most of them have a constant length and that the points in the same direction. The calculated accuracy of the length of the motion vector is between 4 and 8 millimeters. The red arrows on the left figure belong to significant and the blue arrows to non-significant vectors. Only 8% failed the statistical test, assuming a confidential interval of 95%. Now we want to compare our results. On the left, we see the motion vectors obtained by the M3C2 distances, and on the right, the vectors of our method. The results differ in the absolute values. In general, the M3C2 distances show smaller values, besides of some outlines. The median difference is minus 10 millimeters. But also in the direction of the vectors, we can see some difference. When we are looking at the vectors on the top of the rocks on the left, we can see that the M3C2 distances show only the motion vertical to the rock surface. This cannot be seen on the image on the right side. Here, the vectors have approximately the same length and direction, regardless whether they are located on the top of the rock or on the side. Therefore, we can conclude that the presented method provides vectors that are not influenced by the position relative to the rock surface. So in this work, we present a method for the estimation of 3D motion vectors for the monitoring of alpine mass movements. The calculated motion vector are automatically detectable. Furthermore, they enable a spatially highly resolved change analysis. In future works, we want to address the following issues. Until now, we used only the correspondences on the unstable side of the summits. In addition, it could be interesting to see if we can use the correspondence on the stable side to avoid the use of ground control points. Furthermore, we want to test different types of features and also think about doing a dense matching to obtain a dense vector field with a high spatial resolution. Thank you for your attention.